We are going to be talking tonight about this topic of entropy, which is actually a very misunderstood topic in many ways. And we ended last time with something that we called the equation delta G equals delta H minus T delta S. We identified each one of these items in here, and last time we were focused on specifically the subject of enthalpy, right? Delta H. Tonight we are going to focus, tonight we are going to focus on the subject of entropy. Huh, something's not working here. Anyway, let me just go ahead and highlight it. We're going to talk about delta S. There should have been an animation playing here, but for some reason it didn't play. Okay, so last time we talked about decreases in enthalpy. And we ask ourselves, does a decrease in enthalpy mean that a reaction proceeds spontaneously? So let's look at some spontaneous reactions, things that we know that once you start them, they go forward. The combustion of methane, for example. We know that if we light up a Bunsen burner, it keeps on burning. As long as it doesn't run out of methane, we don't need to do anything else to it. The reaction of acid and base, it's a spontaneous reaction. Notice that both of these have negative enthalpies. In other words, they're exothermic. Since we said that the change in energy in a chemical reaction represents the balance between the energy investment in breaking bonds and the energy return in the forming of new bonds, a negative enthalpy means that you've released more energy than you invested, and so you have a surplus, right? So you would think, well, if you have a surplus, if you have a negative delta H, that reaction would be spontaneous. However, if we consider, for example, a process like the melting of water or ice, into water, or a process like the dissolution in water of ammonium nitrate, notice that both of those processes, which we know are spontaneous, right? We know that ice will melt. They are both endothermic, right? So that means that having a negative delta H is not a sufficient criterion to predict if a reaction is going to be spontaneous or not. Here we go to the equation again. So what we're going to do then is we're going to consider the topic here of entropy, and that's going to be the subject of our study tonight. A common thought about entropy is that entropy means disorder. Now, this is okay as a general perspective, but it is not exactly accurate. In general terms, it's okay to think of entropy as disorder, chaos, but it's not exactly accurate. Let me tell you where this idea comes from. Okay, let's say that you get a deck of playing cards, right? You fresh out of the box, you take it out, and you spread it out, and what do you see? Right. All of the cards are in order, right? They're all organized. They're all, all the hearts, all the diamonds, all the spades, they're all organized. And they're also placed typically in a particular order. Cool. Now, Dr. DA will pick out a fresh new deck of cards, slippery as they are, and clumsy as I am. What you're going to get is actually this, a big mess, because I'm going to drop them on the floor. Let me ask you a question. What is the likelihood that in one sweeping motion, I can scoop up these cards and they'll come out exactly the way they were before? Well, magicians do that kind of stuff, but I have news for you. It's a trick, just in case you were wondering. The probability of getting this exact order of cards back from that mess is actually, there's 52 cards in the deck, It's 52 factorial. It's 1 in about 8 times 10 to the 67 possible combinations. That's how unlikely it is. So let me have a more kind of like fun kind of idea. Okay, here is Jorge. Jorge is a typical Southern California teenager. Let's go to Jorge's bedroom in his house and ask the question, is the bedroom likely to look like this? Or is it more likely to look like that? I'll give you one guess. So in other words, the idea here is that, yes, this idea of disorder, of chaos is present in there, but notice that in the case of the deck of cards, the issue was that a disordered, scattered state of cards has more possible distributions of the cards than the one, the single one way in which they were organized in the box. It's 1 versus, like I said, 8 to the times 10 to the 67 different ways that those cards could be organized if they're scattered on the floor. So by sheer weight of statistics, it is more likely that the cards will be scattered than to find them organized in the way they were in the box. Now, you ask, well, how come we did find them in the box like that? Oh, well, somebody put energy into making it that way. And that gives us a hint of where we're going at, the relationship between energy and this property of entropy. Let's do a little history here. This is Hermann von Helmholtz, who was the one that actually presented a mathematical argument for the law of conservation of energy. Remember, we discussed this equation, delta E equals Q plus W, the two ways in which a system can interchange energy with the surroundings is either heat or work. He was the one responsible for that formulation. Later on, Nicolas Carnot studied the working of engines, and he found out that for an engine to perform work, when you supply energy to it, it requires a heat sink. And what that means essentially is it needs a way of releasing heat into. Otherwise, it stops working. The meaning of this ultimately was that the energy input, let's say the gasoline or electricity, whatever you're using to cause the engine to work, that energy cannot be converted entirely into work. Some must be released as heat, and therefore, no engine can be 100% efficient. So later on, Rudolf Clausius proposed that what happens is that in any process, no matter how much thermal energy is released or is there, not all of it is available to be converted into work. There's always some kind of residual energy that cannot be used to do work. And he called this entropy. And there's the equation in the bottom. We're going to come back to that equation later on. We're going to actually derive something similar to that equation that's in the bottom there. Finally, this is the 1860s. It took about 20 something more years before somebody actually put a physical characterization for this property of entropy was, and that was Ludwig Boltzmann. Boltzmann proposed a physical meaning for entropy. He proposed that entropy is essentially a measure of the number of arrangements that are available to a system in a given state. In other words, how are the particles and their energies distributed in a system under a given set of conditions? Okay, let's go and we're going to use an analogy here, and please understand that this is going to be just an analogy, all right? Actually, before we do that, let me go over some concepts here. Okay, let's go ahead and do this, actually. Okay, let's pretend that I have on the top there, I have two tanks connected by a valve, and I start out with gas molecules only on the left side, all right? And I'm going to open the valve and see what happens over time. Now, it's kind of hard to see this one, so I'm going to use a different sketch here. This is going to be a little more sketchy, but I'm going to use boxes. So this is a situation where you have all, let's say I have 4 gas molecules, just for illustration, okay? Don't go deep into the math here, where all 4 of them are in one side of this double chamber. Notice that there's only one way that you can achieve that, right? They're all on the left side. Now, what about having one of the molecules in one chamber and the other 3 in the other one? As you can see, there's several ways of doing that because any one of the 4 molecules could be the one on the other chamber while the other 3 are left. So there's, according to this, let's say 4 possible arrangements. Now, what about 2 and 2? If you do 2 and 2, there's a lot more combinations possible, including the reverse. For example, having 1 and 2 on the left, 3 and 4 on the right, or having 3 and 4 on the left and 1 and 2 on the right. So as you can see, there are a lot more ways of distributing the particles when you have 2 on one side and 2 on the other one. And again, this is this as far as the analogy goes because we're only dealing with 4 little spheres here. And in a real sample of gas, we have gazillions of those particles. But let's say that we call each one of these ways of arranging things, let's call it a distribution, right? It's a 1 and 0, 3 and 1, 2 and 2. And then all of the possible ways of arranging the molecules within that distribution, we're going to call them microstates. Microstates. Here is essentially what Boltzmann said. Let's say that we call W the number of microstates of a system under a given set of conditions. Statistically, he developed the equation that said that this property of entropy, is K, a constant that's been come to be known as Boltzmann constant, times the natural logarithm of the number of microstates. So if we have a change in the system, delta S, that would be the final minus the initial entropy of the system. And if we apply that definition above to this delta S, we find that it's basically K times the natural logarithm of the ratio of the final number of microstates to the initial number of microstates. So for example, let's say that you end up with a system that has more microstates than you started with, then that means that ratio there is going to be greater than 1. That means the natural logarithm is going to be greater than 0, and therefore delta S is going to be positive. K, the Boltzmann constant, is a positive number, by the way. If a system ends up with a final number of microstates that is lower than the initial one, then delta S is going to be negative. Notice that it's interesting that this property of entropy is being defined as a purely statistical function. It has to do with the number of ways in which the particles of a system can be distributed, can be dispersed in whatever container or boundaries or whatever conditions we have set for them. And I think that's very interesting. So let's apply this idea, the number of microstates, the number of ways in which you can essentially arrange the molecules of a system. And let's look at some processes that you can kind of like pretty much by logic deduct that they are representing an increase in entropy. Let's say, for example, the conversion of a solid to a liquid. Makes sense, right? In the solid, the particles are pretty much fixed in position, and so there's very little, lateral or vertical way of them rearranging themselves. When you go into the liquid state, though, the particles, although they are moving close to each other, they are moving, and so they can rearrange themselves in more microstates. Of course, perhaps the most dramatic one will be the vaporization of a liquid. So whereas in a liquid, the molecules are still kind of close around each other and intermolecular forces might restrict some of their mobility and therefore the number of ways they can arrange themselves. When you vaporize the liquid, by definition, an ideal gas, there's no interactions between particles. They are moving about wherever they want, carried by just their kinetic energy. And so you can have many, many, many more microstates of distributing those molecules. Another process that would lead to an increase in entropy would be the dissolving of a solute in a solvent. And I'm going to use the example here of a crystal solute in a liquid solvent. Notice that when we start on the left, the solute is a crystal. It has a very limited way of limited number of ways in which to distribute its particles. But once it's in solution, they get dispersed, and so there's more freedom of movement, and so they're going to distribute themselves in many more ways. Don't forget that in this process, the solvent is also undergoing a change in entropy. So in the end, we're going to have to consider both of them if we want to have a certain idea of what is the actual entropy change. Another one is a change in temperature. A system at a lower temperature, if the temperature is increased, we know because of the kinetic molecular theory, the particles will have absorbed more kinetic energy. They're moving about more, and therefore at any given point in time, they're distributed in more random ways, in different ways, than what they were at the lower temperature. So many different processes, therefore, are responding to this kind of thing. For example, the diffusion of a gas, right? It's just the gas spreads out because if it spreads out, it achieves a greater number of states, and it's a purely statistical process. So one way of thinking about entropy is kind of a measure of the randomness of a system. How randomly are the particles and energies of a system distributed? So if, for example, we consider entropy to be a property that depends on the state, so delta S would be final minus initial. If the change from initial to final state results in an increase in randomness, like the vaporization of a liquid or the increase in temperature of a substance, then what you'll have is the final state will have greater entropy, and therefore it'll be a positive entropy change. As we saw in that previous chart, the physical changes from solid to liquid and liquid to gas allow us to see a sequence in here. For any substance, the solid state is more ordered. In other words, it's less randomly organized than the liquid state. And the liquid state is more ordered than the gas state. So we can build this little sequence here where we can see the entropies of solid versus liquid versus gas. And an example of that would be, for let's say, the melting of ice. Remember, we said this is a process that is endothermic. It has a positive delta H, but it turns out that it also has a positive delta S because we are going from solid to liquid. The final entropy is greater than the initial one. Okay, here are some, I put some pictures here for you. For example, let's say the vaporization of bromine from liquid to gas. We expect the gas state to be higher in entropy and therefore would have a positive change in entropy. The sublimation of iodine solid to gas should also proceed with a positive delta S, right? Okay, you get the idea, right? So let me have you guys practice a little bit here. I'm going to give you some processes, and I want you to think, is this process going to, let me say it again. How does the entropy of the system change for each of these processes? Does the entropy increase or does the entropy decrease? All right, here we go. Ready? Here we go. Condensing water vapor. Okay, think about it for a moment. Condensing means going from gas to liquid. Right. Randomness decreases because the liquid has less ways of organizing or distributing or dispersing or scattering, whatever word you want to use, its molecules. And therefore, this process should proceed with a decrease in entropy. Delta S should be negative, right? All right. How about this one? I'm going to make a supersaturated solution of sucrose, and I'm going to crystallize it. I'm going to form sucrose crystals from a supersaturated solution, right? Randomness decreases again. You're going from a dissolved substance to a solid substance, right? The solid crystal has many, many less ways of distributing its particles. So therefore, this process should also have a negative delta S. All right, how about this one? We're going to heat hydrogen gas from 60 to 80 degrees Celsius. Now, we might think, well, hydrogen gas, it already is probably at a high level of entropy, right? Well, but we're not heating it. So that means that we are now giving that hydrogen gas more kinetic energy and therefore more ways of randomly distributing those molecules, right? And so we would expect this process to happen with an increase in entropy. Delta S is positive. Okay, last one. Subliming dry ice. Sublime means going from solid directly to the gas state. Right. We always know the gas state has much, much more randomly distributed particles. So randomness increases, and therefore, that's right, entropy increases. Now, if someday you take a physical chemistry, upper level course, you're going to be deriving a lot of these equations, and you're going to be dealing with some, heavy duty math. Like I said in other classes, learning chemistry is like learning a language. You can try to become an expert, major in it, learn all the grammar, learn about all the literature, all this kind of stuff, and become, an expert in a foreign language. Or you can just learn the basics just enough to be a tourist and introduce yourself, order food when you go there, and of course ask, where's the restroom? Those are the important things for a tourist in a foreign country, right? So in a way, we're going to kind of like tackle entropy from the tourist perspective, all right? When we studied enthalpy, delta H, we invented a path for calculating the enthalpy change in chemical reactions. We essentially said, well, the enthalpy of formation of an element is 0, excuse me, and the enthalpy of formation of a compound is found in a table. So we can simply add up all the heats of formations of the products and subtract all the heats of formation of the reactants. It's as if we had deconstructed reactants, broken them down into their elements, and built the products from scratch. Notice that we never actually measured the actual enthalpy. We never measured H. All we did was we calculated delta H of different things. Entropy is a little different. We can actually find the value of the entropy for a substance. Like I said, the math is heavy and involved, and we're not going to go into that. So for now, just trust me that we can do that. Here's a table that shows us the standard entropy values for some substances. Notice this is not delta S of formation. This is S. Of course, the superscript 0 or S naught basically means this is under standard conditions. So we can see a few things in here. Let's look at some ideas here that we can see. First of all, we can see that the units are joules per Kelvin per mole. Those are the units of entropy typically. Notice that in all of these cases, S or entropy is a positive number. Notice that even for elements like, carbon or like helium or neon, which when we assign heats of formation, we said the heat of formation was 0. Here they actually have a value. Notice that in all of these combos, if you look at, liquid water versus vapor, bromine, right? The gas form always has a higher or bigger entropy, right? You can see that. Notice the small values for graphite and for diamond. Very, very small values. Again, if we look at the way that carbon atoms are organized in those two forms, right? These are what we call allotropes. Diamond on the left, graphite on the right. You can see a very high level of organization where the carbon atoms are pretty much held in place. So you anticipate these are going to be low entropy situations. Looking at the next pair, methane and ethane, notice that the difference between those two is the number of atoms, or essentially the size. Notice that ethane, because it has more atoms, in other words, more bonds are on which it can rotate and stuff like that, a bigger electron cloud that can be dispersed in different ways, you can see that it has a larger entropy. So the bigger or the more complex the molecule, the greater the entropy. All right, that's another trend that we've seen here. The last one I want you to look at is the comparison here of helium and neon. Notice that neon has a larger entropy. Now, these are monoatomic species. So the only difference between them really is the sizes of the atoms. So the idea would be that the larger atom of a neon would have I guess, more ways of distributing energy amongst, more energy levels, which also is involved in the arrangement of things, of properties of a substance with respect to entropy. So now that we have these kinds of values, I think we're ready to go ahead and do some calculations. Remember, we discussed the first law of thermodynamics, which in words says that energy can be converted from one form to another, but energy cannot be created or destroyed. So in any given process, whatever energy exchange happens in our system is going to be balanced off by a similar change in the surroundings, equal in magnitude, opposite in sign, so that the net change in energy of the universe is 0. Let's now propose the second law of thermodynamics. And this is very important because a lot of people have the idea that science says that everything tends towards disorder. Everything, goes into a mess. The universe is marching towards disorder. Well, you got to be careful with that. Here's the way it works. Here's what the second law actually says. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Okay, notice that we are saying that there is a increase in entropy for a spontaneous process, but it's the entropy of the universe, not necessarily of the system. And this adds another clause in here that says that for an equilibrium process, the entropy remains unchanged. Entropy of what? Of the universe. Remember that the universe is the system plus the surroundings. So that means that for a spontaneous process, the delta S of the universe, which is the sum of the entropy change of our system plus our surroundings, has to be positive. Now, for an equilibrium process, delta S of the universe, which is the sum of the delta S of the system plus delta S of the surroundings, should be equal to 0. Notice that all we're requiring for a spontaneous process is that the sum of these two properties here, these two changes, be positive. That means that even a process that has a negative delta S can still be spontaneous if the corresponding change in the surroundings is bigger and more positive, right? If that's the case, then you're going to essentially absorb the negativity, so to speak, of the delta S of the system and still generate a process that is overall spontaneous, all right? Now, what if you have a calculation that tells you that for this particular process, delta S of the universe is negative? Well, what that means is that the process is not spontaneous in the direction that we're writing it, but it would be spontaneous in the reverse direction. So the reverse of a non-spontaneous process should be a spontaneous process, okay? And don't forget that when we say delta S of system, our system is essentially a chemical reaction, all right? We're not isolating it. We have it in a certain set of surroundings. Like we talked about before, sometimes that reaction is happening in a calorimeter where we can control what is the extent of the surroundings that are going to exchange energy with our system. Okay, time to talk about the third law of thermodynamics. Once more, the math of this is kind of beyond the scope of our discussion. So we're going to say that the entropy of a perfect crystalline substance is zero at the absolute zero of temperature. Remember, in studying delta H, in other words, heats of reactions, enthalpy changes, the only zeros we defined were the formation energy of an element in its standard state. We kind of invented that. But here, we are finding what is a law. This is something that is universally accepted. If you look at this chart, it's going to trace the process of a substance, right? All the way on the bottom left there, you have absolute zero of temperature. These are Kelvin, right? So in other words, if according to Boltzmann, the entropy is K times the logarithm of natural log of the number of microstates, a perfect crystalline substance has exactly 1 microstate at 0 Kelvin, at the absolute zero temperature. And that means that if you plug 1 into that Boltzmann equation, S would be equal to 0. Now, here's the thing. Here's the idea. I have a starting point for the entropy of a substance at any temperature and in any physical state. If I start from 0 Kelvin and I start increasing the temperature, you can see how the entropy begins to increase, right? And as the solid begins to melt, that is also a entropy increase. And the thing is, we have mathematical formulas for calculating what is the entropy at any one of these stages. And because delta S in this case would be final minus initial, but the initial was 0, essentially what you're calculating is the actual entropy value of the substance under those conditions. So I could find, for example, what is the entropy of this substance as a liquid at that temperature? What is its entropy when it's boiling, right? All these kind of things are very, very interesting, all right? So that's what the third law of thermodynamics does for us, okay? So let's go ahead and do this. Let's go do a little practice exercise here. We can calculate, just like we did for energy or for heat, we can calculate the standard entropy of reaction, delta S naught of reaction. The entropy change of a reaction at 1 atmosphere and 25 degrees Celsius. We're going to arbitrarily choose those conditions. Let's say that I have our typical format of a chemical reaction where uppercase letters represent formulas of compounds and lowercase letters represent the stoichiometric coefficients. Well, essentially, delta S is final minus initial. We're in a chemical reaction. Remember, final is products, initial is reactants. So we're going to have the total entropies of products minus the entropies of reactants. Since the standard entropy is given for 1 mole, we're going to have to multiply times the stoichiometric coefficients in order to get the actual formula here. But remember, the idea here is that this is, like it says here in the middle, the summation of the total entropies of products minus the summation of the entropies of reactants, adjusted for the number of moles according to the stoichiometric coefficients in the balanced chemical equation. So let's do a little practice here. What is the standard entropy change for the following reaction? Carbon monoxide and oxygen reacting to form carbon dioxide. Okay, one or two things has to happen here. One of them is they had to give you the standard entropies, or, as I'll show you later, you have to go to Top Hat, Appendix 4, and find what the entropies are. Or, I guess it's a third option, you can simply Google it, right? So let's see what the entropies are for these compounds and elements. Notice that in this type of setup, the entropy of oxygen gas, O2, is not 0. It has a value. And it's actually, up there, right up there with these other ones. So we have CO and O2 who are the reactants, and CO2 who is the product. So let's calculate what is going to be the standard entropy change. Products minus reactants, but remember we have 2 CO2s. We also have 2 COs in the reactants. So let's make sure that we put those coefficients in here. So 2 times the entropy of CO2 minus the sum of 2 times the entropy of CO plus the entropy of O2. Let's put the numbers in there. It's just math at this point. So for CO2, for the products, 427.2, that's 2 times 213.6, minus 395.8 plus 205. That is a total of negative 173.6. Negative 173.6. All right. Okay. Let's do this. I'm going to leave here on the screen this particular slide. So let me show you what happens here for a moment. Let's go here to our let's see, where is our, oops, that's not it. I'm sorry, I'm trying to find my browser here. And I can't seem to find it. Oh, it was right here where the video was. That didn't work. Sorry about that. Don't forget that you have in Top Hat, let me wait till this block of commands gets out of the way. You have these appendices here, and one of them, Appendix 4, has all of these state functions. Last time we looked at the property of delta H of formation. Here on the third column, you had the standard entropies. So you can look them up in there. And remember, again, that anytime you do these kinds of processes, you have the possibility that you're going to end up with different values, all right? In other words, depending on the source, you might get different values in here, all right? So let me go ahead and put this back on here. This is the one that we are working with. And why don't I leave it on? We're going to take a break now for 10 minutes. And if you want to work on it, if not, when I come back, we can ask questions and I can show you some of the results. Okay, so we're going to take a break here. Okay, let's look at these two problems and see what you guys came up with. Probably the numbers that we're going to have in here are different. And sorry about that block in the middle there. But let's see what we get. So this would be 2 times the ozone entropy minus 3 times the oxygen entropy, right? So let's see what that comes up to be. I got minus 137.8. Again, it plus or minus a few joules per mole per Kelvin, right? Bottom one, right? We have essentially the entropy of sodium carbonate plus the entropy of liquid water plus the entropy of gas CO2 minus 2 times the entropy of sodium bicarbonate. And that's what I got. Again, plus or minus a few joules per mole per Kelvin, depending on what was the source of the actual calculation. If you want, you will, you can ask me later on. We're gonna have an optional session later. If you wanna talk about these things, we can go over some of these problems in case you were stuck with anything, okay? All right, so one thing we observe here is notice the transition from oxygen to ozone. And notice that it's negative entropy change. Notice the transition from the reaction, of course, the process from sodium bicarbonate to the right side, where there are molecules of CO2 gas. That one is positive. If you do this a few times, you're going to find some interesting trends that have to do with when gases are produced or consumed. In other words, when one of the reactants or products is a gas state substance. Because of the high entropy of gases, if a reaction produces more gas molecules than it consumes, the entropy change for the reaction is going to be positive. If the total number of gas molecules diminishes, in other words, if the reaction consumes more gas molecules than it produces, the entropy change is going to be negative. Now, what if they're the same? Well, in that case, the delta S may be positive or negative, but delta S is going to be a small number. In other words, in chemical reactions where gases are involved, the production and consumption of gas molecules or elements, gas substances, is going to be the driving force behind the overall entropy change of the reaction, all right? So that's what it is. So this is one thing we can use to check our calculations to make sure that we have the right numbers. For example, let's look at this reaction, the reaction of zinc with oxygen to produce zinc oxide. What would you expect for the entropy change to be, positive or negative? Right, you look at the number of gas molecules, there's one on the left, there's none on the right, the number of gas molecules goes down. So this reaction should proceed with a negative delta S. All right, okay, here we go. This is something that you can derive. I don't think this slide is in your handout, but what I'm going to do is I'm going to post this table when I download the video from this lecture, and you can download it in case you're interested. Top hat goes through all of these derivations. So the entropy of a system increases with increasing temperature. We said that qualitatively earlier. This is the quantitative expression of it. The entropy of a system increases with increasing volume. Remember, an increase in volume allows you to have more room for the molecules to distribute themselves. You predict there's going to be a positive delta S, and there's the formula for it. the entropy of a system increases with decreasing pressure. Now, pressure decrease means increase in volume, therefore you should have a increase. Notice the equation there, it has a negative, but that's because the log of P final or P initial is going to be a negative value also. The entropy of mixing is always favorable. I don't have here a formula for the mixing of, let's say, a solid with a liquid to form a solution, but this is for the mixing of gases. And by the way, those x's in there, x sub 1, x sub 2 represent the mole fractions in the final mixture. Like I said, you don't have to know these things. I'm going to give you these equations on a chart, and there are going to be some questions perhaps in your homework where you're going to be asked about these kinds of calculations. So, but for me, from my perspective, what I want you to know is the qualitative statements. What does entropy increase with respect to temperature, volume, pressure, and mixing? Okay, that's what I need you to know qualitatively. However, go ahead and do your homework and practice using these formulas in math-related problems. Okay, now the second law talked about the change in entropy of the universe. Up to now, we've been talking about delta S of our system, which is chemical reactions. What about the entropy changes of the surroundings? What about them? Well, we're going to consider here two scenarios, all right? Let's say that the process that we're studying, our system, undergoes an exothermic process. Remember, exothermic means that heat is transferred from the system to the surroundings. You would expect that if the temperature of the surroundings is going to be increased by the presence of more energy, more kinetic energy in the particles, their entropy should also increase. So therefore, entropy of the surroundings will increase when you have an exothermic process. Let me give you a few seconds to process that. Think about it. I'm putting heat into the surroundings, which means the surroundings have more kinetic energy, more motion of particles, more microstates, therefore greater entropy. Now let's consider a system that undergoes an endothermic process. So in this case, heat is transferred from the surroundings into the system. That means that the surroundings are losing energy. And if they're losing energy, then that means that their particles have less options in terms of distributing themselves randomly. Therefore, we expect for the entropy to decrease. So for an endothermic process, we would say that the entropy of the surroundings also decreases. Delta S of surroundings is negative. So remember, in an exothermic process, delta H was negative. Delta S of surroundings is positive. In an endothermic process, delta H of the system is positive, but delta S of the surroundings is negative. So we can draw a simple conclusion here. We're going to say that as far as the enthalpy of the system is, as far as the change in heat, delta S of the surroundings is proportional to the negative of delta H. All right? Now, what I'd like to discuss now is the idea of how does temperature actually affect all of this. And to do that, we're going to come back here. Welcome back. And I need to find my doc cam. So I can put it in here for us. There we go. And let's hope that our system holds up here. I do have a bit of a sketchy connection today. Not like, I think that's why the video kind of like got stuck earlier. Okay, let's consider these scenarios here. We're going to consider both the exothermic and the endothermic process. But we're going to consider them. What if the temperature is low? What if it's high? All right. So let's consider a scale of entropy here. I'm going to draw like a scale of entropy here. Okay, let me pull this in a little bit. Oops. No tanto, not that much. So this is entropy. Okay, let's consider the exothermic reaction. Remember, we're going to compare low temperature versus high temperature. And we're going to consider, well, what is the entropy of the surroundings, right? The surroundings, correct? So at low temperature, the surroundings, let's say they have an entropy that's kind of in here. Let's call this SI. But at high temperature, the surroundings should have a higher entropy, right? Because the temperature is higher, so the entropy is higher. Now we are going to have an exothermic reaction happening that is going to pump heat into the surroundings. And as we saw, that's going to cause the entropy of the surroundings to increase. So let's say that the final entropy of the surroundings is this. This is the final one. Let's just abbreviate. This is the initial. Notice that if I was at a high temperature, I'm going to have a change in entropy here. But if I was a lower temperature, the change in entropy is much larger. So in other words, at low temperature, you have a bigger delta S. Low temperature, high delta S. Okay, everybody follow that? All right, let's do this one again, but now let's do it for an endothermic process. Again, we're going to compare low temperature versus high temperature. Again, the low temperature starts over here. The high temperature starts over here. But remember, in this process, which is endothermic, we are taking heat away from our surroundings. We are decreasing the temperature of the surroundings. Therefore, we are decreasing the entropy. So let's say that the final entropy was going to be this one here. Oops, I lost a little bit of my boundaries there. Notice that in this case, my low temperature decreases a little bit, but the high temperature has a longer road to cover, right? They're both negative, right? So in this case, delta S was positive for both. In this case, delta S is negative for both. And typically we said, well, negative means, less entropy, right? But notice that in this case, the condition that started with a lower temperature had a less negative. Remember, when you're talking about negative numbers, remember, the bigger absolute value means the more of a change you have. So this was a less negative delta S. So low temperature, bigger delta S. Low temperature, same thing, less negative. In other words, bigger delta S. Like less negative means, bigger. So the conclusion then is that delta S of the surroundings is inversely proportional to the temperature. So a higher temperature initially will produce a smaller delta S. A smaller or lower temperature to start with will result in a bigger delta S. They're inversely related, all right? Okay, let me pause here in case we have any questions. Give you a few moments to absorb that. And raise your hand, or you can unmute your microphone, or you can put a message in the chat. Nope. Okay, so let's take this stuff we just found and let's go back to our PowerPoint. So let me make this thing, oops, what happened here? Let's talk about this entropy of the universe thing that we started out with when we proposed the second law of thermodynamics. So the second law says that for a process to be spontaneous, the entropy of the universe must increase. The increase in entropy of the universe represents the sum of the entropy change of the system and the entropy change of the surroundings. Right now, because what we're studying is chemical reactions, or otherwise physical processes that we can represent with a chemical equation, we know that at this point, when we say delta S of the system, we essentially mean the entropy change of the reaction, which we can calculate from the standard entropies of all the reactants and products. What did we say about the entropy of the surroundings? We said it is directly proportional to the negative of delta H and inversely related to the temperature. So let's go ahead and make that into an equation. And again, I am skipping a few math steps in here because, like I said, some of the math here is beyond the scope of our discussion. Now, here's what's interesting. We now have an expression for each one of these things here in terms of things we can measure. So let's rebuild the second law here. So delta S of the universe equals delta S of the system plus delta S of the surroundings, and that has to be positive. Let's substitute what we just found out in our previous derivations here. So we're going to substitute for the delta S of surroundings here, the minus delta H of the system over T. The significance of this equation at this point is that we now have an expression of the second law in terms exclusively of properties of the system. Delta S of system, delta H of the system. So we don't have to worry about the surroundings. Everything is in terms of the system. So let's start rearranging this equation to make it a little more manageable. Let's start out by multiplying times the temperature. And so we get T. At this point, let's focus on the middle term here. Forget about the term that has delta S of universe in it. T delta S of the system minus delta H of the system. Again, notice this is an expression of the second law in terms exclusively of properties of my system. So let's do this. Let's rearrange this. Multiply times minus 1. And at this point, because we multiply times minus 1, we had to invert the sign. So from greater than into less than. So we have delta H of the system minus T delta S of the system should be negative in order for the second law to be fulfilled. Okay, this is just math, guys. I just did some math. Along comes Willard Gibbs and says, remember when Carnot was doing that engine and found out that you could never find a perfectly efficient engine because you always had a release of heat and had to find a way of absorbing it, right? And then Clausius said, yeah, what happens is there's always a residue of energy that cannot be used to produce work. So Willard Gibbs comes around and says, well, let's look at the other side. Let's look at the free energy. Let's look how much energy is actually available for productive work. Let's not think about the energy that has to be wasted or used up or the one that is not going to be able to help us make any work. Let's look for the one that's available. And he actually called it available energy, but it is now called the Gibbs free energy, and it has this formula. Gibbs free energy is H minus T delta S. So what happens if a system is undergoing a change? What is delta G? And let's say we're going to do it at constant temperature, because most chemical reactions, we kind of like handle them at constant temperature, right? So delta G would be delta H minus T delta S. The T doesn't change, so you pull it out of the change in here. Oh, what do we have here? Does that look familiar? Yes, it is familiar because we have just derived the equation. That's right. This is the equation where delta G is the change in free energy, the change in energy that is useful or available for the system to perform work. And so, from a second law of thermodynamics that told us that the entropy of the universe has to change, in a situation where there really is no way to mathematically measure the change in entropy of the surroundings, we have now an expression that is in terms of properties of our system. Delta H, which we can either measure or calculate by Hess's law. Delta S, which we can calculate from the standard entropies of reactants and products. And what it gives us is that if that operation gives us a negative value, in other words, a decrease in the free energy, the reaction is spontaneous in the forward direction. Why? Well, because you are decreasing your free energy, which means some free energy is available out there. There's an output of free energy that is available for making productive work. And so the reaction will be spontaneous. Okay? And we are going to leave it there. I think our minds have been blown enough here. Okay, let's go back here to our things. All right, so, you know, that's as far as I'm going to take it today. I hope you enjoyed it. I think it's one of my favorite topics in chemistry is this whole idea of energy and how we can actually do these math operations, half of which I don't remember anymore, but hopefully you've gotten something out of it. Let me see if there are any questions from the audience here. Any questions? No? We are going to reconvene at 7 o'clock. Okay, we're going to reconvene at 7 o'clock. And what I'm going to do then is, if you want me to, I can go through some of the questions in the thermochemistry practice worksheet that we made available on Tuesday night. All right. And again, if you have any questions about tonight's lecture, you can ask them also. Somebody's asking, is the Gibbs energy always negative? The answer is no, it's always negative if the process is spontaneous. Okay, any other questions, either on the chat or by voice? All right, guys, I'm gonna stop the lecture. I'm sorry, I'm gonna stop the recording here. All right.